Okay, so now let's look at the magnetic field created by a long straight current. So we know that Hans Ørsted has found that a current carrying wire will create a magnetic field around it. So now let's see how does the magnetic field lines look like for this current carrying wire. So let's say that we have a current, a very long, in fact infinitely long wire which carries a current I upwards. It turns out that at a distance r from the wire, at this point, let's call it point P, at that point the magnetic field is equal to mu 0 I over 2 pi r. So the magnetic field is directly proportional to current. The bigger the current, the bigger is the magnetic field at that point, and inversely proportional to the distance. The further away you are, the weaker is the magnetic field. The coefficient here, mu 0, is the so-called permeability of free space. This is similar to the permittivity of free space that we had when we discussed the Coulomb's force. Now, of course, the magnetic field also depends on the surrounding material. So if this is not a free space, then we would have another coefficient here. However, in this course, we're going to limit our discussion just to the magnetic field in free space. So in free space, this is the magnitude of the magnetic field. Mu 0 is equal to 4 pi times 10 to minus 7, and the units are Tesla times meter over ampere. You can see that the unit should be Tesla times meter per ampere just from this formula. Magnetic field is measured in Tesla, current is in amperes, R is in meters. So mu 0 has to be in Tesla times meter times ampere. Well, we know that magnetic field is a vector, so it has a direction. So how do we find a direction of the magnetic field created by this current at any point? And this is again done by the right-hand rule. You take your right-hand rule and you point your thumb in the direction of the current. So in this case, the current is going up. The magnetic field lines will be concentric circles around that wire. So you curl your fingers like this of the right hand with the thumb pointing up in the direction of the current, and then this will show you the direction of the magnetic field lines. Well, let's try a few examples. So let's say that we have a current flowing up. Let's say we want to find out magnetic field at this point, at this point, at this point, at this point, and then we're going to discuss the magnetic field here, because it's a three-dimensional structure, and here, at this different point. Using the right-hand rule, I point my thumb in the direction of the current flow and curl the fingers. So which means that my fingers are going into the board at this point, which means that here the magnetic field is pointing into the board. The same thing is true for this point, except for the fact that here the magnetic field is weaker because it's further away. Now on this side, if I continue doing that, you will see that the magnetic field is coming out of the board at this point. And here it's stronger, so it's pointing towards you. Here it's going to be pointing out of the board, but is weaker. What is the magnetic field at this point? Here. It will be pointing this way, to the right. On that side, on the other side of the board, it will be pointing to the left. Of course, you have to imagine a three-dimensional picture, and we can only draw it in 2 dimensions. So this is how the magnetic fields will be oriented if you look at them from a side. So now let's look at what happens to the magnetic field lines and the magnetic field at when we look at the same picture but from the top. Okay, so let's say that we're now looking from here. If we look from the top, then the current would be pointing towards us. So this is now the current. The current is flowing towards you. I can take my right hand again and draw circles using the right hand rule. So, for example, let's say that I draw a circle like this around the current I. Then at this point, the direction of the magnetic field will be pointing straight down. And this is 90 degrees, so this is like a tangential to it. Same thing is here. So I draw this radius and then the tangential to it. And that's the magnetic field at this point, point B. So it's pointing up. At this point, again using the right hand rule, it's pointing to the left. And at this point, it's pointing to the right. Now, in principle, of course, you can find any intermediate point, like for example here. Well, then you just have to draw a tangential line to the radius, and this is your magnetic field at that point. So this is how the magnetic field lines will look like if you look from the top and the current is flowing towards you. What if you want to know the direction of the magnetic field at a distance which is different from this radius? For example, here. Well, it's the same procedure. You have to draw a circle that has exactly the same radius as this one around the current, like this. And then this would be your magnetic field at that point. Now, using the right hand rule again, you find the direction, but note that at this point the field will be stronger than here. So this is a stronger field than this one because this is further away. Now let's look at an example when the current is going into the board. So this is the current pointing into the board. If the current is pointing into the board, then using the right hand rule, the thumb is pointing into the board. I curl my fingers, and so the magnetic field lines are going clockwise. So if I want to know the direction of the magnetic field at this point, what do? I draw a circle like this, and the direction at this point is pointing tangentially to the circle, and so perpendicular to this radius at that point. So this is your magnetic field B. Using the same logic, you can find the magnetic field at this point, and it will be exactly horizontal and pointing to the left. Same magnetic field. If you want to find it somewhere closer, so for example here, again, you draw a circle, and at this point, you draw a tangential line to it, and that is your magnetic field. Note that here magnetic field is stronger than here because it's closer.